Lots of you will probably know Euclid's proof that there are infinitely many primes. It's a proof by contradiction, and what you say is suppose there are only finitely many primes, then multiply them all together and add 1. This number isn't divisible by any of the primes, so there must be another prime divisor not on the list. Boom, we've done it. What I'm going to show you, however, is another proof by the Hungarian mathematician Paul Erdős. He thought of this as a proof from a book, by which he meant a proof which was so beautiful it came straight from God's own book of proofs. It's more complicated than Euclid's, but the arguments along the way are really interesting, which is why I want to explain it. We're actually going to prove something stronger, which is that if you take the reciprocals of primes and add them all up, the sum is infinite. You can't have an infinite sum with only finitely many numbers, as with finitely many numbers it has to stop at some point. So by proving the sum is infinite, you imply that there are infinitely many primes. Like Euclid, we will also use proof by contradiction. So let us assume that the sum of the reciprocal of the primes actually does not sum to infinity. This means that the sum does stop at some point. By saying this, we can say that at some point in the sum of the reciprocals of primes, there is a point at which the rest of the numbers added together is less than a half. So what does that mean? This is a rather difficult concept, and when I tried to get my head around this, I found a simple example which helped me understand the broader concept. So let's say that the set of P, which is of all the primes that exist, consists only of 2, 3, 5, and 7. So that means that the only prime numbers out there are 2, 3, 5, and 7. Then pk plus 1 is equal to 5, since we can easily work out that 1 over 5 plus 1 over 7 is smaller than a half. And we know that the first term is 2, that's for sure. And that as Pn increases, the value also increases. Therefore, if we take the reciprocals are decreasing as you go up. So no matter how big the set of P is, there must be a point at which 1 over pk plus 1 plus 1 over pk plus 2 and so on and so forth is smaller than a half. Let us divide our set P into two groups. One of small primes, which is P1, P2, P3, all the way up to Pk, and large primes as Pk plus 1, Pk plus 2, Pk plus 3, and so on. I will also define three new sets. Set S, whose elements are all the whole numbers from 1 up to an arbitrary number n, and set A, which contains elements of set S, where the element has only small primes as factors, and set B, which contain elements of set S, where the element has at least one large prime factor. From the above, we can write out a few statements. A union B equals S, the number of elements in S equals n, A intersect B is an empty set, and the number of elements in A plus the number of elements in B equals the number of elements in S. So if you were to represent this as a Venn diagram, it would look something like this. So let's first focus on set A. Elements A of set A can be written as their prime factorization, and since they only have small primes as factors, i.e. P1 to Pk, they can be expressed as P1 to the M1 times P2 to the M2 times P3 to the M3, and so on up to Pk to the Mk. Note, however, that their power can be to the power of 0 as well, so the corresponding Pn would just be equal to 1. You can extract the square factors from each A, which is essentially grouping together the highest even powers of each prime factor, which we shall call alpha squared. For example, if A equals 2 to the power 7 times 3 to the 3 times 5 to the 6, then alpha squared would be 2 to the 6 times 3 to the 2 times 5 to the 6. The remaining part of A would then be comprised of P1 to Pk to the power of either 0 or 1. Therefore, there are two possibilities for each of P1 to Pk, so there are a total of 2 to the k possibilities. Set A is a subset of set S, so therefore the largest possible value of A has to be smaller or equal to n. Since A can be expressed as alpha squared times some value, then alpha squared has to be smaller or equal to A, as alpha squared is largest if that sum amount equals to 1. Therefore you can get alpha squared is smaller or equal to A, which is smaller or equal to n. So alpha squared is smaller than or equal to n, and alpha is smaller or equal to the floor function of root n. The floor function takes the integer value since we are just dealing with integers. From this, you can count the maximum number of elements that can be in set A, which is the floor function of root n times 2 to the power of k. And now on to counting the number of elements in set B. We can do this by adding the total number of numbers from 1 to n that is divisible by each individual big prime. We can do this by finding the floor function of n divided by pk plus 1, pk plus 2, pk plus 3, and so on and so forth. The number of elements in set B is smaller or equal to this number, since we have almost definitely double counted many of the numbers. We can also say that the floor function of n over pk plus 1, pk plus 2, and so on forth is smaller or equal to just n over pk plus 1 plus n over pk plus 2, etc., etc. We can then factorize out n, and we get the sum of reciprocals of the large primes, which from earlier we defined as strictly smaller than a half. Therefore, the number of elements in set B is strictly smaller than n over 2. Let's recap on what we know so far. We know that the number of elements in set S equals to n, the number of elements in set A is smaller or equal to the floor function of root n times 2 to the k, and the number of elements in set B is strictly smaller than n over 2. Working with two variables is really annoying, so we just need to find a convenient value to make as our n, which can be anything. So I'm going to make it 2 to the 2k plus 2. Now we can find the number of elements in A and B, which is strictly smaller than the floor function of root 2 to the 2k plus 2 times 2 to the k plus 2 to the 2k plus 2 over 2, which we get by subbing in 2 to the 2k plus 2 instead of n. And you can simplify it like this. Wait, so something isn't quite right here. We got the answer of 2 to the 2k plus 2, which, as above, equals n, which, as we found out earlier, is equal to the number of elements in set S. So, does that mean that the number of elements in set A plus the number of elements in set B is strictly smaller than the number of elements in set S? If you remember from earlier, we did find out that the number of elements in set A plus the number of elements in set B equals the number of elements in set S. So therefore, our conclusion must be wrong. So, if our conclusion is wrong, then our original assumption must be wrong, which was that the reciprocal of the primes does not sum to infinity. Since this assumption is wrong, we can therefore conclude that the sum of the reciprocals of primes does in fact sum to infinity, which therefore proves that there are an infinite number of primes. We've done it!